What if the fiery heart of our planet is slowing down? For billions of years, Earth has been fueled by a superheated, molten core, a powerhouse driving everything from the continents we stand on to the invisible magnetic shield that protects us. But what if that engine is starting to lose its fire? New research is hinting at a chilling possibility. The Earth's core might be cooling down, and if it is, what would that mean for life as we know it, hidden deep beneath our feet, thousands of kilometers below the surface? A profound change might be unfolding, a silent, geological shift that could one day reshape our world. Scientists are now wrestling with the radical question, is our planet's core actually cooling? The implications are far more dramatic, far more fascinating than you might imagine. Stick with us as we journey to the center of the Earth to uncover the truth. Think of the Earth as a living, breathing organism. It has a heartbeat, a rhythm, a source of energy that keeps everything in motion. That heart is its core. Imagine a sphere of solid iron, hotter than the surface of the sun, suspended within a vast ocean of swirling, liquid metal. That's the Earth's core in a nutshell. The inner core is a solid ball, mostly iron and nickel, under such immense pressure that it can't melt, despite being over 5,000 degrees Celsius. Surrounding it is the outer core, a fluid layer of molten iron and nickel. It's this churning, liquid outer core that generates our planet's magnetic field. This entire system is the engine of our world. So, the central question we're re-exploring today is not just a geological curiosity, it's about the future of our entire planet. Is this powerful engine losing heat? And what does that even mean for us surface dwellers? So, how can we possibly know what's happening so deep inside the Earth? We can't exactly drill a hole and pop a thermometer in there. Instead, scientists act like planetary detectives, piecing together clues from a distance. One of their primary tools is seismology. By studying how earthquake waves, or seismic waves, travel through the planet, they can map out the core's structure. These waves change speed and direction when they pass from the mantle to the liquid outer core, and then to the solid inner core. It's like a planetary scale ultrasound, giving us a picture of the deep interior. Another key piece of evidence comes from our planet's magnetic field. Since the liquid outer core generates this field, any changes in its strength or behavior over time can hint at changes in the core's temperature and fluid dynamics. And finally, there's mineral physics. In hypersur labs, scientists try to recreate the insane conditions of the core, squeezing and heating minerals to see how they behave. This helps them understand how heat is transferred from the core to the mantle above it. Recently, some of these studies have produced controversial findings. One line of research suggests that the boundary between the core and the mantle is allowing heat to escape faster than we previously thought. Another study, analyzing ancient rocks, indicates that the Earth's magnetic field has been weakening over geological time, which could be a sign of a cooling outer core. It is crucial to understand we're talking about two parts of the core. The solid inner core is actually growing as the liquid outer core slowly crystallizes and freezes onto it. This very process releases heat, ironically helping to power the convection in the outer core. So, the cooling isn't a simple shutdown. It's a complex, dynamic process of change at the very heart of our world. Now, let's unpack the big implications. When you EAR core cooling, your mind might jump to a new ice age, but that's not what scientists are talking about. The real effects are more subtle, yet profoundly important for the geology of our planet. A cooling core would mean less heat flowing into the mantle above it. The mantle isn't a static layer of rock. It's a viscous fluid that churns in slow-motion convection currents over millions of years. This movement in the mantle is what drives plate tectonics, the shifting of continents, the creation of mountain ranges, and the eruption of volcanoes. A cooler core could, over immense timescales, slow down this convection. This might lead to less volcanic activity and fewer earthquakes. Essentially, the geological pulse of our planet could begin to slow down. But the most significant consequence lies with our magnetic field. This field is our planet's shield, deflecting the vast majority of harmful charged particles streaming from the sun, known as the solar wind. Without it, our atmosphere would be slowly stripped away, and the surface would be bombarded with deadly radiation. The strength of this field is directly tied to the vigorous churning of the liquid outer core, which is powered by heat escaping from the inner core. So, a cooling core would inevitably lead to a weakening magnetic field. We aren't talking about it vanishing tomorrow, but a gradual decline over millions, or even billions, of years. We're not facing an immediate, global, cooling disaster, but rather a fundamental geothermal shift that would redefine our planet's long-term future. So, let us fast forward and imagine what life might be like on a planet with a much cooler core and a weaker magnetic shield. This isn't a scenario for our grandchildren, but for a distant, almost unimaginable future. The primary concern would be increased exposure to solar and cosmic radiation. Our magnetic field currently funnels these particles towards the poles, creating the beautiful auroras. With a weaker field, more of these particles would reach the surface globally. This would pose a significant threat to life, potentially increasing rates of cancer and genetic mutations. It could also disrupt our technologies, frying satellites and power grids. Over even longer geological time, a weaker field could allow the solar wind to erode our atmosphere, just as it did on Mars, which lost its global magnetic field billions of years ago. A thinner atmosphere would change everything: ocean currents, climate patterns, and the ability of the surface to hold on to liquid water. It's a stark reminder of how interconnected every part of our planetary system is, from the core to the sky. But before anyone panics, let's emphasize the timescale. The changes we're discussing would unfold over hundreds of millions, if not billions, of years. The Earth's core is a massive reservoir of heat, and it won't be giving up its energy anytime soon. Humanity will face countless other challenges long before the core's temperature becomes a direct problem. This is a story about the ultimate geological destiny of our planet, not an imminent catastrophe. It's a journey into the deep future. This brings us to the frontier of Earth science. The truth is, there are still huge unknowns. How fast is the core really cooling? How does the exchange of heat and material at the core mantle boundary truly work? Our models are getting better, but the Earth's interior remains one of the most mysterious places in the universe. Scientists are constantly working on new ways to peer into the deep. This includes deploying more sensitive seismometer networks, analyzing the planet's magnetic field with ever greater precision from satellites, and pushing the boundaries of high-pressure experiments in the lab. Every new piece of data helps us refine our understanding of the engine that makes our world habitable. The story of our planet is still being written, and its deepest chapter is just beginning to be explored. What do you think the far future holds for Earth? Will technology one day give us a way to influence our own planet's geology? Let us know your thoughts and theories down in the comments. We love reading your ideas about these big questions. If you found this journey to the center of the Earth fascinating, please give this video a thumbs up and consider subscribing to our channel for more deep dives into the wonders of science. Thanks for watching, and we'll see you in the next one.